Well, good morning everybody. I think we're about ready to go. Firstly, thanks very much for coming along this morning. It's great to see so many people here. My name's Bob Hill. I'm the Executive Dean of the Faculty of Sciences, and I'm going to take you through the first 10 minutes or so this morning, basically with the theme of trying to explain to you why science is a good idea and what we've done to try and make science more relevant into the future. It's important for our faculty to be relevant. I mean, we really are. It's an important issue for us that we train students that are able to make a real contribution to society. So it's worth reflecting on what this means. Scientists are responsible for many of the things that make life great in the 21st century. But the challenge we face now, globally, is to bring everybody up to a reasonable standard of living and maintain that well into the future. And that's a problem that's hardly been addressed. We live in Australia where lifestyles are great, where standard of living is great, but that's not true globally, and we can't ignore what's happening in the rest of the world. When I was growing up, the biggest issue facing the world on a global scale was the Cold War. We were worried, I was worried as a child, about the threat of nuclear war. That was probably the first genuinely global threat that we faced as a species. There was a solution to that, and the solution, even though it was hard to implement, was relatively easy. Make people get rid of their nuclear weapons. That hasn't happened, but the threat has largely gone away because the nuclear stockpile has declined and people have learnt to talk to each other in a better way than they did back then. However, we have a set of global challenges that are facing us into the future that are not quite so easy to deal with, and that's really what's facing you as students coming into this system. This slide points out what some of those problems are. Population. I'll talk about population again in a moment. There's more people every day, and it's a long way off stabilising globally. We have to feed those people, and that's a challenge into the future, and it's a challenge few people understand the magnitude of. We want to do that in a way that protects the biodiversity that we have out there. We're losing species by the dozen on a weekly basis. And we have to do all of those things in a world that's changing, where the climate's changing, and it's not changing in a way that's going to favour what we're trying to achieve. These are serious challenges that you can't solve locally, but everybody locally has to make their contribution. Here's one way of describing that challenge, part of that challenge. And I think in this single graph you can see that science has got a role here which unfortunately the media and much of the general public doesn't fully appreciate. The black line on this graph is human population growth over the last 200 years roughly. In the space of 200 years we've gone from 1 billion people to more than 7 billion people. We passed that mark just recently. Consider that we'd been around as a species for about 200,000 years before this. It's taken us 200,000 years to get to 1 billion people, 200 years to get to 7 billion. That's an astonishing rate of increase. The United Nations pays a lot of attention to this, and they make predictions into the future. The green, the yellow and the blue lines give you their predictions based on worst case, medium case, best case. I can leave you to work out which they think is the best case and which is the worst case. But there is a potential by the end of this century for us to be sitting around 12 billion people, nearly double what we are now. The red line, which sits underneath this, is based on the axis to the right, is the rise in atmospheric carbon dioxide, the greenhouse gas that people hear about most, that they know about most. There is serious debate still in the media and amongst politicians as to whether the rise in carbon dioxide has a human cause. Have a look at that graph and figure out for yourself whether you think human population growth has had an impact on the carbon dioxide rise. And that carbon dioxide rise is not subtle. It's been a massive increase. Back in 1800 it was about 280 parts per million. Now it's pushing 400 parts per million. We're pushing up towards doubling the amount. The impact of that on climate is significant. Little known fact about climate change: if we melted all the ice on the planet, and that's not going to happen in your lifetimes, any of you, but if we did, the Sydney Harbour Bridge roadway would be at sea level. 75 metres of sea level rise. So we're interested in problems like that, we're concerned by problems like that. That's the challenge for us. So what did we do? What have we done with our curriculum to try and make students ready as graduates to face these problems and deal with them? We began by redesigning our curriculum from first principles, and we started out by looking at our research strengths. The Faculty of Sciences is an incredibly strong research faculty. We rate with the best in the country, with the best in the world in the quality of our research that we produce. So we decided to really push our research strengths down into our teaching as hard as we could. We did that by redesigning our curriculum around the 10 big questions. And the 10 big questions are specific to our faculty. They are the 10 research questions that we believe we contribute to most strongly. Any science operation in the world could come up with their own set of 10 big questions. Many of them might be common to the ones we have, but this is our set, and as far as we can see, we're the only science operation that's done this. We then pushed those questions very heavily into our curriculum, and this became what we call our ELFS project, Enhanced Learning in First Year Science. I guess that makes me the head elf. Quite a few elflings here today to support. Here's our 10 big questions. And you see just by looking down through this list that this is an interesting mix of questions. Some of them are blue skies research questions. How did the universe begin? Scientists have to deal with questions of this nature. It's what we do as human beings. How does the earth work? What is life? How did life evolve on earth? But then we get to the more interesting questions, which are much more applied questions, much more socially relevant questions, now and for the future. And the wording of these questions is worth considering. How do we unravel the causes of disease? Why does climate change? We're not saying anything about how to fix climate change, we're saying we can tell you why climate changes, rather, not how. We do a lot of research into the past. When we know climate changed thousands of years ago, tens of thousands of years ago, millions of years ago. That's what we know about. You go back and look at what happened in the past, you can much more easily predict what's going to happen into the future. And so on as you run down through the list. We have the agricultural campus out at Waite, so quite legitimately we can address the question, how can we feed the world sustainably? If we continue with agricultural production the way we are right now, by the middle of this century, people will starve on a global scale. We must increase agricultural production significantly between now and the middle of the century. The 10 big questions have been in place for some time now, and I pay tribute to the advertiser who have supported us very strongly with this. Every Tuesday during school term time, there's an education lift out in the advertiser, and on the front page of that, they feature the Can You Believe It series, which is written mostly by our students now, our research students, sometimes by our early career staff, and in the last 12 months or so, it's always featured one of the 10 big questions. The redesign of our curriculum, which really started in 2010, was assisted significantly when we moved to a fully interactive hardware option, which is the Apple iPad. These were given to students in 2011, and we've repeated that this year with no strings attached. We had no expectations about how students would use them. We had the expectation students would know how to use them and use them well, and that's proven to be the case. It's been a highly successful project for us. Why did we do this? We knew that students would carry an iPad with them. If anyone looks at science textbooks, they're about this thick, you need about 4 of them at any one time, and they weigh about 5 kilos each. No student regularly brings those textbooks into university, but they will bring an iPad, and we have electronic copies of the books which can be put onto them. iPads are fantastic for internet access, and we made sure they're all 3G enabled, so if students wanted to, they could access the material that we were producing anywhere. And at the time, there were quite a few relevant apps for education. Now there's a whole lot more. What happened as a result was something that I didn't expect. The results were certainly better than I anticipated. Here's some of our student feedback. The yellow bars on these graphs are from 2010, the year before we introduced this new curriculum. The blue bars are from 2011, the first year that we had students with the 10 big questions, the new curriculum and the iPads. You can see on the left-hand side here, and you excuse me while I get my glasses, this is really small print. The question was, all things considered, how would you rate the effectiveness of this person as a university teacher? And this is in one of our, in fact, it's in all of our first year courses. You can see in 2010 with the yellow bars, we weren't doing too badly. The higher the percentage there, the more students rated the teacher highly. But in 2011, we had an outstanding outcome. The vast majority of students believed that our teachers were at the absolute top end. Perhaps even more interesting is the question on the right. Overall, I'm satisfied with the quality of this course. You can see again in 2010, most students were in the 71 to 80% bracket. In 2011, it shifted fully 10% to the right, the increase in satisfaction from students at the new curriculum that we were producing. And likewise, in a different survey, we asked students about the use of the iPad. We asked them in 2 years, 2011 the first time, 2012, when we had a slightly better idea of how to make good use of the iPads. And this is the result we got. You can see again, the vast majority of students are at worst neutral and at best very positive about what we've introduced into sciences. So what have we achieved? A clear understanding of the relevance of the curriculum, I think, has been a very important outcome. Teaching as a partnership. We're really interested in the whole notion that you learn best if you're engaged in the learning process. Unfortunately today I'm standing here just talking to a large number of people sitting in front of me. This would be a much better experience if you all had the opportunity to interact with me as we're doing it. That's the way we teach as often as we can inside the faculty. Removal of dependence on hard copy textbooks. This is a particular issue for me. Not only are the textbooks big and cumbersome, but they're very expensive. It would cost $1,000 to buy all new copies of textbooks for first year science. The first year we had the iPads, the cost came down to $600 because we had electronic books and you could buy the electronic books cheaper than the hard copy. We're now to try and get rid of the cost of textbooks altogether, and we think we can do it. There's a chance we'll do it for next year. Certainly it'll be cheaper again, but certainly sometime in the future we'll get rid of the cost of textbooks, and I hope there's no one from the textbook industry here, because in my view they're Satan on earth. They take an awful lot of money out of students that can't afford it, and the sooner we can get away from that kind of reliance on a very expensive option to give students content, the better off we'll be. We gave students instant and universal access to email, the internet, and all online sources of information. And that was fantastic for us because there's a lot of first year students and it meant that we could keep in contact with them regularly. Prior to that, it was very hard for us to do it. So what do we expect from incoming students into sciences? Well, our contribution to this is that we'll make science available to all capable students. That comes back to the cost issue. I'm very interested in seeing that we get the best people here, the most committed people here. I don't want it to be based on whether you can afford to do it. To those of you that have the right motivation, we'll help you to become a professional scientist with two critical skills. And it's important to understand what these skills are. You can get content anywhere now. If you want to know about science content, go to the internet. It's all there. The best universities in the world put their course content up free now. You're not going to get any better content here than you're going to get free on the internet. And that's true for any university in the world. What do we do with that content? We're going to train you to have the capacity to ask the right questions to solve complex problems, and we're going to train you to have the capacity to solve those problems. Those are not trivial things. That's what you take the content and you train yourself to do, to be a problem solver. And everyone that employs our graduates fully understands that we produce people who can make things work, who can solve problems, who can think up questions that other people can't think up. That's a fantastic skill set. And we need those skills more than we've ever had before. That comes back to those big problems facing us into the future. If you can't solve those problems, if you can't contribute to it, then you're not making as great a contribution as you have the potential to do. Here's a quote from a person called David Warlick, who's running a project internationally in education. For the first time, we're preparing learners for a future we cannot clearly describe. I think that really sums up the challenge we're facing. We've certainly made our best efforts to date to solve that problem, and I genuinely hope that a good majority of you here today will be there in the future to share that with us. Thank you. Now, I'm all microphoned up here, so you just have to hold on while I switch over.
Thanks, Bob. Hi, my name's Simon Pike. I'm the Associate Dean for Learning and Quality in the Faculty of Sciences, and I'm going to follow on and just give you some idea in terms of the structure of some of the programs of study that are available to you within the faculty. I'm going to talk about 3 particular classes because we have a range of different offerings depending upon where you think you want to head. The first one is the Bachelor of Science, and I'm sure that you've all heard of the Bachelor of Science program. It is the most flexible program that we offer. There are a range of different areas, and this is just a sample of the range of areas that you can actually pursue within this program of study. So for example, if you want to be, I'm a chemist, so there I am, I exist, makes me feel a lot better. If you want to pursue a range of different offerings, for example, if you want to pursue biochemistry and chemistry, then the Bachelor of Science allows you to do that. Conversely, you can also pursue spatial science and ecology within the Bachelor of Science. Again, it's a very flexible program and it does allow you to explore and determine your own destiny. That's its biggest asset. We also have a relatively new version of the Bachelor of Science. This is our 3rd year of offering, will be next year, the Bachelor of Science Advanced. And this has been specifically set up for students who are right at the top of the tree, and particularly ones that are actually interested in pursuing and engaging with us in the research agenda of the university. So the Bachelor of Science Advanced does have an ATAR of more than 95 for entry. My bad, I actually noticed that we actually haven't changed the nomenclature on our slide. That shows you something as well. It also provides a significant range of choice, not as much choice as the straight Bachelor of Science. It's a little bit more restricted, but having said that, there are some hundreds of different pathways that you can choose to pursue through the BSc Advanced. The key differentiator between the BSc and the BSc Advanced is a 2nd year subject and a 3rd year subject in the Advanced program, which are called Principles and Practice of Research. And they are only available to the advanced students. So that is actually where students in their 2nd year of study will engage with us, the staff, and learn about the research process, and in their 3rd year actually engage in the research process themselves as well. So that's the prime driver for this particular program of study. In terms of a pattern of study, what will you be doing if you enrol in either of those 2 programs? Well, in fact, the 1st year of study is the same for both the BSc and the BSc Advanced. You choose 3 out of these broad disciplinary areas: biology, chemistry, geology, maths and physics. The only difference, and in fact the prime question here for helping you work out which space you want to sit inside, is do you actually want to pursue physics as a pathway of study right through your program? And if the answer is yes, then there are certain things that you need to do because you actually have to take 1st year maths alongside 1st year physics. If the answer is no, then effectively what you would usually choose is you would choose 3 from the 4 at the top, so biology, chem, geology and maths. And in fact, most of our students fall into the category biology, chem, geology, or maths and physics and one other science. So we try and make it as reduce the number of options available to you as far as possible in your 1st year of study, both from our purpose to build a cohesive body of students who all have a common background of knowledge, also to help you actually work out where you want to go. These are foundational sciences that everybody needs to engage in. The 4th course in 1st year is Principles and Practice of Science, and this is actually a course which is not specifically about the content of science, but it's more about how science works, how it operates. Very important and aspect there, particularly around learning how to write in the scientific space. And that's a very important skill because every scientist needs to be able to communicate and particularly be able to write well. Second semester has the same pattern, and there is a space for one elective in second semester, and there's a range of different things that you can insert into that space. So that's the general programs of study, the most flexible programs. The second tier that we have are what are the so-called named degrees. So this would be Bachelor of Science, bracket Animal Science, or Bachelor of Science, Biomedical Science. These, as you can see, are more defined. So these actually have particular outcomes in mind for each particular cohort of students. So for example, if you enrol in the Bachelor of Science High Performance Computational Physics, yes, that's what you are going to be. That's the direction that you are heading in at the end of your program of study. So there's less choice. These are more scaffolded. Okay? So that's the key difference. It's just a little bit, it's a pre-planned program of study, if you will. A couple of ones to pick up on here, particularly veterinary bioscience. So that is the first half of the veterinary science pair of degrees. So the Bachelor of Science Veterinary Bioscience, followed by the Doctor of Veterinary Medicine, actually then gives you the qualification to practice as a vet. Anybody here interested in vet? Couple, okay, good. And there's as you can see, this actually spans the range of different areas that the faculty has strengths in, and almost all of those, in fact all of those programs of study, at the heart of those programs, there is at least one of those 10 big questions sitting there as a question in terms of what's the point of this program, what's it trying to achieve. These are all tied to our research agendas as well. The third set of programs are what we would define as specialist programs of study. And again, these have a very strong outcome. For example, the Bachelor of Agricultural Sciences, obviously that's really obvious where it's going. The Bachelor of Food and Nutrition Science, again, that has a very specified group of courses that make it up. It's a very cohesive program of study. I need to point out, it doesn't qualify you to be a dietitian. Okay, I just need to keep saying that to everybody every year. It is a much broader degree program which is around the science of nutrition. And then the fourth one down the bottom, the Bachelor of Viticulture and Enology. This is a 4-year program, both in terms of grape growing and wine making. So it's a combined degree that that services both of those needs. The key thing about these 3 programs of study is they are much more prescriptive. So there's less flexibility. You know where you're going from day one, and so there's less choice in terms of what you study along the way. In terms of employment, science is one of those interesting degree programs that doesn't actually have a vocation at the end of it that says, this is what a scientist does. In fact, people with science degrees finish up in a whole range of different places. They may well finish up travelling into the research pathway. They may well go out and work commercially. They may well finish up becoming teachers. And let me say, we need good science teachers. That's a really, really good outcome. The food industry, very strong. In South Australia, animal and agricultural science, very, very strong, and lots of career opportunities in that space. So these are all things which are directly related towards the types of science that you would study here. There's also a field of other career options which are not that obvious. So for example, government policy, in the media and around science communication, around the law, even just general, that's a misnomer, but in business and commerce. People with a science training are actually very highly sought after because they can think well. So that's a really, really important characteristic, and one of the things that we will actually cultivate in you as you move forward. And you can see that, so there's this series of things which are obviously related to doing a science degree, and a series of things at the bottom that it's not so clear that the science training is leading you towards, but this is actually based around the other skills and attributes that you bring with you, and it actually comes out of learning to think like a scientist, and that's very much what our programs of study will build in you. If you're interested in possible careers, just follow from the university front page, go to the Faculty of Science, Future Students and Careers. There's a whole lot of information there. I did check on one of the major places that we actually use as a metric for this one. It's not linked from here, but nature.com, Nature Jobs. Worldwide, there were 11,500 possible openings for scientists last week. So there is very, very good career prospects out there. And let me tell you, get a science degree, it is actually a part of travel the world and practice as a scientist. I've done that myself, and many of my colleagues have as well. Last thing, one of the things that the university does, you may have seen the Adelaide Approved program. So this is the magic target. You get 75, we will make you an offer. Okay? It's a guaranteed offer. If you get an ATAR of 75, you will get an offer into a science program. Now, I must point out that there are a couple of exceptions to this one, and particularly the veterinary bioscience. That has obviously, it's much more competitive, but certainly we're trying to actually make it easier for students and take some of the pressure off to get that score at the end. 75, you will actually get a place within a science program of study. More information, certainly go to the university front page. Ask us, either up in Benithan Hall, so there's a sciences area up there, or down on the Bar Smith lawns. There's many of the disciplines down there. You can use the Student Centre. There's an information night coming up in December, so keep your eyes out for that. Change of preference night will be the 3rd of January. So after you've got your results, so if you want to make some changes, you can come onto campus, talk to us about your choices at that point in time, and then sign up at that point. I do hope that we'll actually see many of you here next year. I'm very happy to take some questions at the end, so I'll just stay down the front. I encourage you strongly to talk to as many of the people who are actually out on the stands today as possible. Ask the questions that you want answered. That's the biggest opportunity that you have today. I hope you have a terrific day. I hope you stay dry and have a lot of fun. Thank you very much. The other thing that I'll just mention, there are tours happening now, so a day in the life of a student. Now these are student-run tours for students. So if you actually want to see what our facilities look like, I strongly recommend that you actually go on one of these tours. There's one leaving shortly, I think. Yes, so there'll be one leaving shortly just out in the foyer. Thanks, folks. Have a great day.